Hey everyone, welcome back. This will be lecture B of lecture 29, part B, and we'll continue in this lecture our discussion of power series. Okay, so where we left off previously was we left off with examples where we were given a function, given a power series, right? So we were given a power series. Such as f of x equals the sum from n equals 1 to infinity of x to the n over n. So given a power series such as this one, and asked to identify its interval of where it converges. So we're given something like this, and asked to identify where the function converges, right? And so that involves identifying R, right? So identify R, the radius of convergence. Okay, and then secondarily, and this was sort of the most recent feature, I brought into the fold. The most recent thing was to not only identify the radius of convergence, which tells you the interval open, but to test the endpoints for convergence as well. And so, for example, this function here, we see r is equal to 1. It's centered at 0. Right? So naively, we would say the interval of convergence is at least -1 to 1. But then when we, so that would be item 1, and then when we come into item 2, we would notice that, oh, in fact, the lower endpoint produces convergence as well. The upper endpoint does not, right? So the interval of convergence is actually -1 inclusive up to but not including 1. Okay, so that's kind of where we left off. And so what we want to do now in the second part is to kind of transition into power series representation of functions, right? And then like all of the things that would spin off of that. So naturally, when we start to talk about representing functions using power series, the question of the characteristics of the function come into play, right? So continuity, differentiability, can we integrate, etc. Right? And so the following theorem kind of addresses these types of questions, right, for power series. So let's jump into this theorem. Okay, so if a function defined by, all right, and it's going to be a power series here, f of x equals the sum from n equals 0 up to infinity of a sub n x minus c to the nth power. And we know what this is equal to, of course. This is a0 plus a1 x minus c plus a2 x minus c squared plus ... Okay. So if you have this function and it has a radius of convergence r greater than 0, of course, then on the interval c minus r to c plus r, f is differentiable, and therefore continuous. That kind of comes with the package, right? And moreover, the derivatives and antiderivatives can be given in general, right? The derivatives and antiderivatives are, right? And so starting with the derivative f prime of x, okay, it's going to be equal to the sum from n equals 1 up to infinity. So notice the index changes, And then it's n times a sub n x minus c to the n minus 1 power. Okay, right, and so we know, of course, that that's equal to a1 plus 2a2 times x minus c plus 3a3 times x minus c squared plus dot dot dot. Right, so you can kind of see the pattern there. Okay, and so this is, again, just the first derivative, right? And so basically the constant term vanishes with the first derivative, and the coefficients all of the subsequent terms are decremented by 1 in terms of their power, and then of course you get the coefficients will change. Okay, they'll advance by whatever the exponent previously had been. Okay, so it's very easy to remember it when it's in this form. Okay, what about the integral? So then the integral of f of x dx is going to be equal to c plus, there's a constant of integration there that we'll have to think about, and then it's going to be n equals 0 to infinity of, the a of n will stay the same, but then you're going to have x minus c to the n plus 1 power, all divided by n plus 1. Okay, and so it looks like that, and then just write out the first couple terms. So just put the c up front, and then plus a0 times x minus c plus a1 times x minus c squared over 2 plus, and I'll just leave it at that. Okay, so we'll spit like that. Okay, so this is the derivative and the integral of power series. Okay. Okay, perfect. Right, so that's the first theorem, and we'll be working with these quite a bit here in this section. And so that is the form of the derivative and the form of the integral of a power series. And so a few things to note for this. So the radius of convergence, this is kind of part of the theorem still, actually. The radius of convergence of a series obtained by differentiation or integration, a power series, is the same as the original series. Okay, so that's nice, right? So if r is the radius of convergence for f of x, then it is for f prime of x and integral of f of x dx as well. All right, so if the radius of convergence for the original function is r, whatever that happens to be, 1, 10, 50, whatever it is, then that same radius of convergence is going to be applicable for the derivative and for the integral as well. Right, so that's very convenient, and I suppose probably as you might expect too. Okay, the thing to note, however, is that while the radius is the same, the interval may vary. Okay, so obviously what does that mean? Well, the power series is going to remain centered at C, and so if the radius is the same, but the interval may be different, that basically means the endpoints could vary. Okay. All right. Okay, so we'll get into some examples where we explore this a little bit, but that's the basic result of the theorem, right? So you've got given a power series, standard power series like this, we can write explicitly what the derivative and integral of the power series will be. And further, we know that the power series, whatever the radius of convergence of the original series happens to be, it's the same for the derivative and the integral as well. However, the interval may vary. The radius is the same, but the interval may vary. Okay. Okay, so a function. So let's kind of recap. So a function defined by a power series behaves pretty much like a polynomial. Okay, a function defined by a power series behaves a lot like a polynomial. Okay, a function defined by a power series and that's a good thing, right? That it behaves a lot like a polynomial, right? Because polynomials are continuous, right? And we have to say on the interval of convergence, i.e. on its domain. And the derivatives and antiderivatives can be determined by differentiating and integrating term by term, right? So it's a simple thing like a polynomial. You'll have a series of terms. You can just integrate, differentiate them separately, and add them all together, right? So that's true as well for a function defined by a power series, right? So derivatives and antiderivatives can be determined term by term, right? So hopefully people are following that second statement, right? So if my polynomial is f of x equals x squared plus 3x plus 2, right? Then the derivative is the derivative of the first term plus the derivative of the second term, right, like this. And also the integral is the same way, right? It's the integral of x squared plus the integral of 3x plus the integral of 2, right? That's what we mean by derivatives and antiderivatives can be determined term by term. It's simple. That's a fact of polynomials, right? They can all be broken up nicely like this. Okay. So let's take a look at an example and see what this looks like in practice. So example, we'll let f of x equal the sum from 0 to infinity of x to the n over n factorial, one we've seen. Okay, so then what's the derivative here? So f prime of x is equal to d dx of the sum right, which is basically d dx of, let's just write out some of the terms. There will be 1 plus x squared over 2 plus x cubed over 3 factorial plus and so on. Okay, and we know that that's equal to d dx of 1 plus d dx of x plus d dx of x squared over 2 plus, right, so on. So let's put one more in there. d dx of x cubed over 3 factorial plus so on. And so then differentiating this, you get 0 plus 1 plus, what is this? This would be 2 times x over 2, and this would be 3 times x over 3 factorial, right? X squared, sorry. And then dot, dot, dot. And so we see that this is 1 plus x squared over 2 factorial, okay, and plus, and then the next term would be x cubed over, we don't have it in here, but 3 factorial, right? So notice here, this is this cancels out and you get that. This is a 3, would cancel with the 3, but you'd still be left with 1 times 2. So you have the 2 factorial. The next term, I should have put it in, would be like plus, what would it be? 4x cubed over 4 factorial. Right? And that's where you get this one. Okay. So notice that this is actually, in this case, in this example, f prime of x is the same as f of x, isn't it? Right? This is the same as what we started with. And compare this with this. It's identical, isn't it? Right? So why? So here, f prime of x equals f of x. Right? Do we remember where this power series came from? Oh, can we remember where this came from? You might remember. Obviously, if you've watched the videos, you might remember. But this actually turns out to be, so this power series n equals 0 to infinity of x to the n over n factorial is the power series for e to the x. Right? And so it makes sense that when we differentiate it, we get the same thing, right? Because, you know, this makes sense because when we differentiate e to the x, what do we get? We get e to the x, right? So naturally, its power series is an exact, is going to be a facsimile, basically, of e to the x. And so when we differentiate it, we ought to get the same function back, and we do. Very nice. That's not going to be true in general, but it's true of this one. Okay, so very, very, very cool. Let's take another example. Let's look at another one. So let f of x equal the sum from n equals 1 to infinity of x to the n over just n this time. So in this case, the series looks like this. It'd be x plus x squared over 2 plus x cubed over 3 plus dot, dot, dot. So for this one, what we want to do is let's find the interval of convergence for f, but also for f prime and integral of f. Okay, so let's find all of these, the interval of convergence for all of these. And the point of this exercise is to see that, at least in this case, how the radius can be the same for all three of these functions, but the endpoints may vary. Okay, so first let's go ahead and find f prime. We're given f, so let's find f prime of x. Okay, so that's going to be the derivative of the sum n equals 1 up to infinity of x to the n over n. Okay, and so that is basically going to be, let's see, it should be, I mean, you could think about just differentiating each of these, and so you get 1 plus 2x over 2, so 1 plus x plus x cubed. So every time the denominator is going to cancel in the derivative, isn't it? It's going to look like that. And so it's really just, in this case, it's going to be equal to the sum from n equals 1 to infinity of x to the n minus 1. Right? All right, so that's the derivative. Now, what about the integral? Let's calculate the integral of this function. So the integral of f of x dx. Well, just kind of using the form, we know this is going to be c plus the sum from n equals 1 to infinity of, and then it's going to be x to the n plus 1 over n plus 1 times n. Okay, so that's the integral. So all we did, so remember the original function is x to the n, so f of x was equal to n equals 1 to infinity of x to the n over n, right? And so to integrate, we would just basically, increase the exponent. Well, it's going to be c plus increasing the exponent by 1, and then dividing by that as well. So that's where you get the n plus 1 on the bottom times the n, right? So kind of see that? Okay. All right, and so the integral of f of x dx is equal to this. N equals 1 to infinity of x to the n plus 1, and I'm going to write n times n plus 1. And so what do the first couple of terms look like here? Well, you got the c, and then it's x squared divided by 1 times 2, right? Plus x cubed divided by 2 times 3, plus x to the 4th divided by 3 times 4, and so on. So it kind of looks like that. Right, so a very different function. Very different from, seemingly from the derivative and from the original. Okay. So now let's move into the discussion of, we want to find the interval of convergence for each of these. So let's take a look at that. So we'll consider the integral of f of x dx first. Okay, so let's consider that one first. And we'll use the ratio test here again. So ratio test. And so what we need is the limit as n goes to infinity of a sub n plus 1 over a sub n. Okay, and what we want to know is for what values of x is this less than 1. Okay, and so let's put in the actual, substitute in the actual term. So I'm going to put the n plus 1 term first. And so this is going to be x to the n plus 1 plus 1, so it'll be x to the n plus 2 divided by, now instead of n times n plus 1, it's going to be n plus 1 times n plus 2. So that would be a of n plus 1. And then again, I'm going to invert and multiply for the denominator so that I don't have to have that extra step in there. And it's just going to be the nth term, right? So it's just basically this piece here. So it'll be x to the n plus 1 under n times n plus 1. All right. And so what's this amount to? This is the limit as n goes to infinity of, now the x, you're going to be left with 1x on the top, right? And then the n plus 1s will cancel. So up top you've got n times x. And down below, this cancels away, that cancels away. You've got n plus 2. Okay. So that's what that limit is. And so this is going to converge. This is going to be this. You can do the same exercise as before, as in the previous examples that we've done, where we divide everything by n. So nx over n divided by n over n plus 2 over n. Right, and you get the limit from n as n goes to infinity of the absolute value of x over 1 plus 2 over n. So when x gets really, or when n gets really large, this goes to 0, and this is basically equal to the absolute value of x. Right, and in order for the series to converge, that this has to be less than 1. Right, so here we can see what we can see here that r is equal to 1. Now let's consider the endpoints, right? So this is a series centered at 0, so we're talking about at least -1 to 1. Right, now the question is, what about the endpoints? Okay, so let's consider those endpoints. Okay. So consider the endpoints. So when x is equal to 1, we'll start with that. What can we do? Well, there's a number of things you could do. One way to do it, kind of the way I kind of like to do it, is to just pull out the integral test in this case, right? We can use the integral test. There are other ways you could approach this as well. This is a nice recap of the integral test, though. So what we need to check is that the integral from 1 to infinity of 1 over x times x plus 1, we need to see that this is less, that this converges less than infinity. Okay. And so this is going to be the limit as b goes to infinity of 1 to b of, and then I guess I'll just rewrite it, x times x over 1 over x times x plus 1. Okay, can we integrate this? Yes, we can. Right, so this is, you could use a partial fraction decomposition. I'm going to kind of skip over that part, and we'll see that this is the natural log of x minus the natural log of x plus 1 from 1 up to b. And so the limit as b goes to infinity of, and this would be the natural log of x over x plus 1 from 1 up to b. And so what do we get there? The limit as b goes to infinity of natural log of b over b plus 1 minus the natural log of 1/2. And so when b goes to infinity, this just goes to basically to 1, right? And so, and this is obviously finite, so we'll just write less than infinity. Okay, and so this indicates that, so we see that the upper endpoint is in the radius, is in the interval of convergence. Okay, right, and we see that because the integral test converges, right? The integral, when we think of the nth term as an integrand and we integrate from 1 to infinity, we get some convergence. So now, what about the lower endpoint? Well, this whole argument would work for the lower endpoint as well, right? The only difference here would just be that I would put a -1 here, right? So certainly if +1 converges, then -1 also must converge, right? Everything would be really the same. So finite, just kind of negative, right? So lower is into, so the interval is -1 up to +1. Okay? And that's for the integral of f. Okay. Okay, so there's our first answer. Now what about the others? Well, let's look at the derivative next. Okay. So for f of x, f prime of x equal, now what was the function? It was n equals 1 to infinity of x to the n minus 1. Okay, so the question here is, for what values of x does this series converge? Let's again use the ratio test. This one will be simpler to work out. So by the ratio test, we'll get the same. We can confirm that the interval is the same. So the limit as n goes to infinity of, so a to the n plus 1 over a to the n, and plugging in the actual term, we get, so this would just be x, I'll just write it, to the n minus 1 plus 1, and then divided by x to the n minus 1. Okay, and so what do we get here? We just get the limit as n goes to infinity. Now this would just be n, wouldn't it? So it's n over n minus 1. And so you get the absolute value of just x, right? And this is less than 1 whenever the absolute value of it, whenever the absolute value of x is less than 1, right? So confirming that r is equal to 1, right? We kind of knew this from the previous theorem, but it's nice to just kind of confirm it. Okay, now what about the endpoints? We can again use the integral test on this really quickly. Right, so the integral of from 1 to infinity of 1 to the x minus 1 dx. That's what we'd want to test. We want to see that this diverges or converges, and that'll tell us, what we need to know. And so the integral from, this will be the limit as b goes to infinity of the integral from 1 to b of, and now this is just 1, right? So it's really just dx. And so that's the limit as b goes to infinity of x from 1 up to b. And so this is going to be the limit as b goes to infinity of, now plugging in the integration limits, it'll be b minus 1, won't it? Now what happens here? Well, as b grows without bound, this becomes an increasingly large number, minus 1, so this is infinite. So the upper bound diverges, right? And hence the upper bound is not in the interval. Okay. All right. Now, what about the lower bound? What about x equals -1? Does that work the same way? Well, it's not as straightforward with the integral test. So for the lower endpoint, we can simply note that when x equals -1, the sum from n equals 1 to infinity, this is the derivative again. Oh, shoot. So when x is equal to -1, f prime of -1 is the sum from n equals 1 to infinity of -1 to the nth power over n. And now this is just an alternating series. Right? It's an alternating series with right now, it's definitely true that a sub n plus 1, which would be equal to 1 over n plus 1, is less than or equal to 1 over n, which is a of n. Right? And so the alternating series test says that if you have this, and this is also something we can see really quickly, the limit as n goes to infinity of a of n, which is the limit as n goes to infinity of 1 over n, this is equal to 0, obviously. So if you have those two things with an alternating series, then the series will converge. So the series will converge when x equals -1, right? So for f prime of x, the interval of convergence is different than for the integration, for the integrated function. So for f prime of x, the interval of convergence is -1 to +1, like this. Okay. Okay. Now recall what we saw on the previous page. We saw something different. That for the integral, both the lower and upper bounds were involved. Both the lower and upper bound was involved in the interval of convergence. All right, so let's write that in here just to make sure that we're tracking that. For the integral of f of x dx, the interval of convergence is -1 to 1 inclusive, both sides, right? So they're different. Same radius, different intervals. The endpoints vary. Right? Now what about the original function? Where does it fall? Let's see. We can do that one really quickly. For the original function, okay, again, ratio test. So the limit as n goes to infinity of a of n plus 1 over a of n. Right, and so you may have to look back a page or two in your notes, but the function is n equals 1 to infinity of x to the n over n. Okay. Okay, so that's the function we started with. And so the ratio test would be n, limit as n goes to infinity of, and it would be x to the n plus 1 over n plus 1 times n over x to the n. So multiplying by the reciprocal. Okay, and so this is quick to see that the radius is the same, so it would be just x times n over n plus 1. And so this is going to converge. So again, same trick, divide everything by n, and you'll see that this converges when x is less than 1. When the absolute value of x is less than 1. Okay, so this is literally from here to here, it's the exact same step as what we saw in the previous first example of the derivative function. All right, so clearly we've established that r is equal to 1 again, right? We expect that. Again, we just stated it in the theorem. We didn't prove it, so it is good to at least work an example to confirm that it does hold, at least in an example, right? That doesn't tell you that it's true. You should really see the proof, but the proof is a little bit time-consuming and lengthy. I do recommend you look into it. But now what about the upper endpoints? Integral test can be used to look at the upper endpoint. Right, we just have to confirm that the integral from 1 to infinity of 1 to the x over x dx converges or diverges. You have to confirm, which is it, to figure it out, I guess. So this is the limit as b goes to infinity of 1 to b integral, and then I guess I'll write 1 over x dx. And I probably could have done this in one step, but that's okay. This is the natural log of x. Now, x will be positive. It's technically the natural log of the absolute value, but we're only talking about positive values here. So this is the limit as b goes to infinity of the natural log of b minus the natural log of 1. And this is going to definitely be infinite. Okay, and so what does that mean? Well, it means that the upper endpoint is not in the interval of convergence. So the upper endpoint is not in the interval of convergence. Okay, so we know at least that our, so we've got this, right? This one is still in question, but we know the upper one is open. Okay, now what about the lower endpoint? This is again the same situation as the previous. This is an alternating series, and we simply have to, would simply have to note that fact, and that's all we need. So for the lower endpoint, when x equals -1, f of -1 would be the sum from n equals 1 to infinity of -1 to the n over just n. And so this is an alternating series. Like before, basically. Okay, so here we would have a convergence, and the interval, overall the interval of convergence is -1 up to 1, but not including 1. Right, so for f, the interval was -1 up to 1, open on the top. For the derivative function, what was it? It was open on both ends. And for the integral, what did we have? Closed on both, right? Okay, and in each of these three cases, we confirm that R is 1. Obviously, we can see that R is 1 here, but the radius of convergence was the same for each of these functions, but the intervals varied, specifically with regard to the endpoints, right? And that's exactly what the theorem says will happen. Okay. All right, very good. That was kind of a long example. Let's take a look at another type of function that can be represented by power series. And so this is the geometric power series. Let's talk about the geometric power series. So think of the function, so consider the function f of x equals 1 over 1 minus x. Okay, it's a function we've certainly encountered in Calc 2 a lot. Here, if you look at this, this function, the way it's written here, it pretty closely resembles the sum of a geometric series. So recall that if you have a geometric series, it looks like this. Sum from n equals 0 up to infinity of a times r to the n. And we say that that's going to be equal to a over 1 minus the absolute value of r, where r is less than 1, right? So remember, r had to be smaller than 1 in absolute value in order for the series to converge. When it does converge, this is what it converges to. So this looks a lot, these two are, obviously resemble one another. So letting, if we were to let a equal 1 and r equal x, then a power series representation for 1 over 1 minus x centered at 0 could be arrived at pretty quickly. Okay, so we can write this as a power series. Let's do that. Let me flip the page here. Okay, so what we would say is a equals 1, r equals x. Then what we would have is 1 over 1 minus x is equal to the sum from n equals 0 up to infinity of x to the n, right? So this would be like your r to the n. So a is 1, r is x, and right. So this would look like 1 plus x plus, and that's equal to 1 plus x plus x squared plus x cubed plus dot dot dot. Okay, and so this is of course only where x is less than 1 in absolute value. All right, so it's important to note, right, that this power series here, what we see here, this part, only is equal to this on the interval of convergence, on its interval of convergence, right? So this function is not going to be infinite. So if I were to plug in, the number 5 for x, then this is going to be an infinite number, clearly. But if I plug in the number 5 here, then this is not going to be an infinite number. This would be 1 over negative 4, right? So this is true only on the interval of convergence, right? So in the case of the geometric power series, what we mean by that is the interval -1 to 1. Right, -1 to 1, and specifically open. Okay, and so so that can be an obvious, something that people obviously notice. You're like, wait a second, if I plug in a 5, this is definitely infinite, and this is not. How are they equal? It doesn't work outside the interval of convergence. All right, so this does not converge outside of this interval, and this equality doesn't isn't valid outside of this interval. Okay, so there we go. So we could, I mean, so again, this is based on this particular interval, but we could represent this power series on any interval we like. It doesn't have to be, the interval centered at 0. We could center the power series elsewhere. So we can center the power series wherever we like, right? That's kind of the next step. So for example, let's center it at x equals -1. Right, so for that we'd say 1 over 1 minus x, right? We'd write that's equal to 1 over, now what I'm going to do is I'm going to add and subtract 1 from the bottom, so it'll be 2 minus x plus 1. All right, so just to keep in track here, so this is 1 over, and then it was 1 minus x, and then I say plus 1 minus 1. Right, and so the 1 plus 1 gives me the 2, and then I've got negative x minus 1, so I factor that out and I get x plus 1. Okay, so I'm just adding 1 minus 1. Okay, and so this could all be, we could divide everything down by 2, and we get 1/2 on the top, and then 1 minus, and what do I get over here? X plus 1 over 2. Okay, and so this is equal to my a over 1 minus r, right? So a is equal to 1/2, and r is equal to, the other piece here, the x plus 1 over 2. Okay. All right. And so, so this is where is this gonna converge? Well, it's going to converge, so this will converge when x plus 1 over 2 is less than 1, right? Which is to say that x plus 1 is less than 2. Okay, so when this is true, when x plus 1 is less than 2, the absolute value of x plus 1 is less than 2, we have a power series here. Right, and so it's going to be true in this case that 1 over 1 minus x will be equal to the sum from n equals 0 up to infinity. And then again, it's just writing this, it's ARN, so we just plug in those values that we basically derived up above here. So our a is 2. Sorry, our a is 1/2. Yeah, so I'm going to write it like this. I'm going to write it like 2 times negative x over 2 to the nth power. Okay, and so that's going to be our power series, and so we could expand this out, and you'd see that this is 2 times, let's see here. Oh, you know what? I wrote this wrong. This is 1/2. What am I writing that? Oh, I wrote it all wrong. Okay, hold on a second. Sorry about that. I got ahead of myself. So this is n equals 0 up to infinity of our a. Just follow the template here. 1/2. R is x plus 1 over 2 to the nth power. Okay, so this is all I needed to write. I was thinking of something else. And so you could expand this, right? This is basically 1/2 times, and then it's going to be 1 plus x plus 1 over 2 plus x plus 1 squared over 4 plus and dot dot dot. Okay. And this is true whenever when x plus 1 is less than 2. Okay, absolute value of x plus 1 is less than 2. So what is that interval? Well, it's the interval of, right, so if I add 1 to both sides of this, I get -3 up to 1. Okay. All right. So this has a radius of 2. Okay. But it's centered at -1. Okay, so that's this example. All right. Very good. Let's take another. Let's do another kind of example, sort of like this. Let's find a power series for, let's see, 4 over x plus 2, centered at 0. Okay. So, we first want to, this is our f of x, so let's write f as in the form a over 1 minus r, right? So f of x equals 4 over x plus 2. Okay, so this is going to be equal to, let's kind of reverse it, so it's 4 over 2 plus x. The x will be our r, and so we need to figure out what that is. So let's divide everything down by 2, first of all, because this needs to be a 1. So that'll be 4 over 2 over 2 over 2 plus x over 2. So it'll be 2 over 1 plus x over 2. Okay, and then technically we would have 2 over 1 minus negative x over 2. Okay, and so this is going to be, so a over 1 minus r is equal to 2 over 1 minus negative x over 2. Right, and that obviously implies that a is 2 and r is negative x over 2. Okay, perfect. And so then the power series here, the power series for 4 over x plus 2 at c equals 0 is, well, we can just write it out here, 4 over x plus 2 equals, then it's going to be the sum from n equals 0 up to infinity, and this is again just a times r to the n. Okay, and so here's we're going to have a 2, that's our a, and then r is what? Negative x over 2 raised to the nth power. And this is, we can see this is 2, and then this is going to alternate. All right, you got the negative in there, so it's going to alternate. So it'll be positive initially, and then it'll be negative. So 1 minus x over 2 plus x squared over 4 minus ... See how it goes. Perfect. And so then this series, when will this converge? So where is this valid? When will it converge? Well, it's based on a geometric series, right? And so it converges. So it converges when r is less than 1, i.e. when negative x over 2 absolute value is less than 1. Okay, and so that means it's centered at 0 and its radius will be 2. Right, because you would have this. So this would be like that, right? So this is true. Oh, I'm so sorry. So this is true when x is in the interval -2 to 2. So r is equal to 2, c is equal to 0. Okay. Perfect. Okay, so that is a power series for this particular function, and it's a geometric power series. All right, excellent. Let's see here. Let's jump to the next theorem. So we've got all of these power series. What what can you do with them? So we know we can differentiate them. We know we can integrate them. We know that the radius of convergence will remain constant. The intervals may vary, however. What about like exponentiating them? What about multiplying by a constant? What about adding and subtracting them? So let's take a look at that. So theorem, let's let f of x equal the sum a of n x to the n, and we'll let g of x equal the sum of b of n x to the n. Okay, so these are two power series. Then there are a couple things here. So first, what if we so we can plug in an x, but what if we plug in k times x? What happens? Well, you get the sum from n equals 0 to infinity of a sub n, and then it's going to be k to the n, x to the n. Right, so that's pretty standard fare, right? If I plug in a k times x, then I'm raising both of those to the nth power. Right? That's pretty standard. Nothing too surprising there. What if I exponentiate? So what if I have f of x, and then I raise x to the n power? Well, here again, pretty standard thing, right? So I'm plugging in an exponentiated value, and so we know that it would look like this. What happens if I add or subtract? What about f of x plus or minus g of x? Well, again, this is a sum, right? So they work nicely together, don't they? This would be a of n plus or minus b of n. Just as you would expect. Now, these are all, of course, this theorem has the power series centered at 0. You would maybe see different results if f was centered somewhere and g was centered elsewhere. So be careful of that. We'll maybe talk about that in a later session. Let's do an example. Again, I guess, something to note, of course, is that, these operations can change the interval of convergence for, the resulting series, right? So if I add or subtract two series, it may change my interval of convergence. Let's see this example will kind of address how that happens, or what you can expect, right? And so if I have, first example will be n equals 0 to infinity of x to the nth power, and I want to add a power series to that, n equals 0 to infinity of x over 2 to the n power. Now, this one here converges on -1 to 1. Okay, now what about this one? Well, this one converges, has a wider radius. It's -2 to 2. Both of them, as you can see, are centered at 0. Okay, and so that makes sense. But the theorem says that when I add these together, I can just add the terms, right? So this would be like 1 plus 1 over 2 to the n, so the an part, and then times x to the n power. And so it turns out that this guy here has a radius of convergence of, an interval of convergence of -1 up to 1. Okay, so at least from this particular example, you might be inclined to say, okay, it must be like the intersection of the interval, right? Because -1 to 1 is also in this one, right? But then this one is wider, and that extra piece that isn't contained in this one is also not present in the sum. And so in general, that is the case. So in general, the interval of convergence, I'm just going to write interval of convergence, the IOC, of a sum is the intersection of the interval of the IOCs. Okay, of the original two. Okay, so the interval of convergence is -1 to 1 here. The interval of convergence is -2, 2 here. So the IOC is -1, 1 and -2, 2. The intersection of those two is going to be the IOC for the sum. Okay? All right. Yep, so that's kind of the general principle here. And yeah, let's take a look at, so let's kind of take, so given this fact, we can develop a whole bunch of additional power series, right? So given the properties that we just talked through, right? So namely the sum and difference, the multiple, scalar multiple, and the exponentiation, we can use that to whip up a whole bunch of other geometric, or a whole bunch of other power series, many of which will be based on the geometric series. So let's look at an example. Let's find a power series for f of x equals 3x minus 1 over x squared minus 1. Okay. And so something like this. Now you can look at this and notice pretty quickly that, you know, it's basically a polynomial on top and bottom, but the degree is higher. And it's actually a squared polynomial on the bottom. And so this is a good candidate for partial fractions, like a partial fraction decomposition. So 3x minus 1 over x squared minus 1, right? And you can do a partial fraction decomposition on this, and when you do, you get 2 over x plus 1 plus 1 over x minus 1. Okay, so clearly this could be factored into these two pieces, and the numerators can be found. Okay, right? And so given this, given the fact that the function can be written as a sum like this, and that each of these look geometric, you can use what we just learned. So these two look geometric. Okay, and so we can use the previous technique to identify a power series for each of them separately. So we'll take each of them separately. All right, so we'll start with the 2 over x plus 1. Well, this would be equal to 2 over 1 minus negative x. And so that's going to be my a over 1 minus r. So a is equal to 2. R is equal to negative x. And so the series here, so 2 over x plus 1 would be equal to, the series is n equals 0 to infinity. Again, it's just ar to the n, so it'll be 2 times negative x to the n. Right, and probably a better way to write this would be n equals 0 up to infinity of 2 times negative 1 to the n times x to the n. Okay, and this is true when x is less than 1. What about the other one? Well, the other series is going to be based on 1 over x minus 1. Right, and so this one we could write as negative 1 over 1 minus x, which implies that a is equal to negative 1 and r is equal to positive x. And so in this case, 1 over x minus 1 is equal to the sum from n equals 0 up to infinity of, it's basically just negative 1 times x to the n. So I'm going to put the negative out front and write it like that. Okay, and again, this is going to converge when absolute value of x is less than 1. Okay, and so I can add them together. So then what we would say is, you know, the original function, f of x, was equal to 3x minus 1 over x squared minus 1, which we saw was, could be decomposed in, using partial fractions into 2 over x plus 1 plus 1 over x minus 1, right? And then each of these separately we found a series for above, right? So let's put that on the next line. So the first one, we found this guy, right? So this would be the sum from n equals 0 up to infinity of 2 times negative 1 to the n x to the n. All right, and then the second piece here, we found this guy, right? So then we could say plus a negative sum n equals 0 to infinity of x to the n. Okay, and all of this can be combined. And what do we get when we combine this? Well, you can just kind of combine the an part, right? So it'll be 2 times negative 1 to the n, and then it's just minus 1, isn't it? Times x to the n. So this is a power series for this more complicated function, but it's based on just this partial fraction decomposition of that more complicated function and then just the sum. So the interval of convergence is going to be the same as the previous two, right? These both converge. They're centered at 0 and they converge within a radius of 1. And so the interval of convergence here is negative 1 to 1 as well. All right. Excellent. Excellent. Okay. And so then one last topic from this section, and these are going to be kind of like another couple of examples, but it's possible to also identify power series using integration. This is something that comes up often, and it's kind of interesting. So let's find a power series. We're going to find a power series for a particular function f of x equals the natural log of x, and we're going to center it at 1. Okay. So this is the example. So in a previous example, from a previous example, we saw that 1 over x was equal to the sum from n equals 0 up to infinity of negative 1 to the nth power times x minus 1 to the nth power. Okay, so we could integrate both sides of this. So if we integrate 1 over x and we integrate this sum, what do we get? Well, we get on this side the natural log of x, right? And on this side, we know how to integrate a power series. We get c plus, and this is going to be the sum from n equals 0 up to infinity. And we're going to put the negative 1 there. And then it's going to be x minus 1 to the n plus 1 power over n plus 1. Okay, so it looks like that, right? Okay, and so notice that if we let x equal 1, right, we can conclude that c must be equal to 0. So if we let x equal 1, we can see that, right, so natural log of 1 is equal to c plus the sum n equals 0 up to infinity, negative 1 to the n, and then here's where you get it, 1 minus 1 to the n plus 1 over n plus 1, right? So these are all 0. And so that shows you that c is equal to 0, right? And so then we can say that the natural log of x is equal to the sum from n equals 0 up to infinity of negative 1 to the n times x minus 1 to the n plus 1 over n plus 1. Right? So this is a power series for natural log of x. And how do we find it? Well, we knew a power series for 1 over x we integrate 1 over x to get natural log of x and integrate the series as well, right? And so, clever. It's a nice one, right? Let's do one more like that. Let's do one more example. Okay, let's find a power series for g of x equal to the arctan of x, right? Centered at x equals 0. Right? Kind of doing centered at x equals 0. Okay, so again, just kind of, these are a little more complicated, but just recall the derivative of the arctangent. Recall that the derivative of arctan x was equal to, what's that? 1 over 1 plus x squared, right? So you can look that up if you don't recall it, but it is the case. And so we know that if we have f of x equal to 1 over 1 plus x, we know that that's equal to the sum from n equals 0 up to infinity, of negative 1 to the nth power times x to the nth power, right? And so instead of x, let's sub in x squared, because that's what we have up here, right? So this is going to imply that f of x squared would be equal to 1 over 1 plus x squared, of course, which would be equal to the sum from n equals 0 up to infinity of negative 1 to the nth power, and then this is going to be x to the nth power squared, right? So this would be x to the 2n, right? Got to be careful there. And then by integrating, right, what happens when we integrate? Well, the integral of 1 over 1 plus x squared dx, right, is equal to arctan of x, which is kind of what we're after in the beginning, and it's going to be equal to the integral of this power series. Okay. Okay, so what is this then? That's what we need to know. So the arctangent of x is equal to, now how do we integrate this? Well, again, just it's going to be a sum, and the negative 1 to the n is just going to stay there. It's a constant on each of the terms. And then instead of x to the 2n, we're going to have x to the 2n plus 1. And then we have to divide by that. Okay, and then of course you've got a plus c. I should usually put the plus c up front, but now I'll put it on the back. Now, and just like before, this is centered at 0, so let's plug in 0. And when we do that, we get arctan of 0, which is 0. And then this is obviously all going to be 0 as well. And so c will be 0. So plugging in x equals 0, we see that c equals 0. And so the arctan of x can be written as a power series n equals 0 up to infinity of negative 1 to the n power of x to the 2n plus 1 over 2n plus 1. Okay, and so that is our power series for the arctangent. And so you can begin to imagine how, there are many clever ways to develop a power series for a function. Obviously, we've just touched upon them here, a handful of them. There are many ways that we haven't really looked at. So that's where we'll end this section, and then the next section will be the last lecture of Calc 2, and we'll discuss in that section Taylor and Maclaurin series. A very cool high point to end on. Okay, so take care, and we'll see you next time.